Welcome back. This is the fourth video on splines and nonparametric regression methods. We're going to cover smoothing splines today in this video, but before we get into it, some of you might be feeling a little bit of mathematical overload from the previous video, and I thought it would probably be best to just start out with an example that will, motivate you to carry on, to persevere through this. So what I told you was we'd like to have this method. What we dream about is a method that I can just dump the data into, press a button, and it will automatically detect what the relationship is. So whether it's a regression problem or a classification problem. So I decided to construct an example. And so I made myself kind of a messy real function. So you can go, if you're curious what that real function was, here it is. But the true function is shown in green. And so this is the true f, that green function. And I tried to make this as kind of ugly as possible in terms of, my God, we changed slope, and then we changed slope again, and then it looks like we flatten out. It's what happens there. It's going to approach an asymptote. But this is a very complicated function with a lot of changes in curvature and slope. So I then added some normal errors with a certain standard deviation. So we really have homoscedastic errors, so the spread around this is always the same. Well, now what I'd like to do is just show you how easy it is to find that function using a spline. So in R, there's a command called smooth.spline, and this returns the coordinates of this spline function. So it returns the coordinates, therefore I pass it off to line. And I say, let's give it color red, and I'll make the width a little bit bigger. And so that smoothing spline function approximated the green curve using the data, only the observed data that I gave it. And you have to admit this is an incredible approximation. That red line is right on top of the green line, and I didn't have to do anything. So think about what I would have had to do back earlier in the course. I'd have to find the right transformations, and this function is so messy that there is no simple transformation that I can make to get there. The other oopsie, didn't mean to do that. I'm not sure what to do to get out of that. All right, that works. ggplot also offers a spline command. So if I use ggplot, the geom points gives me the raw scatter plot. CEX equals 0.5 just means make the dots a little bit smaller. But then I can add a smoother to it. So we've seen this before in the class. If I said method equals LM, you get a line. If you say method equals GAM, you get a smoothing spline. And again, this function is remarkably good. I didn't superimpose the true function, but you can see we've captured the middle of it. So I hope at this point you are motivated to persevere through the math. I thought I'd give you one more example. This is from some of my work with the local news initiative. And this is a graph that I've been showing literally around the world to different audiences, presenting the local news initiative findings. So one of the things that we found is that local news enterprises, if they want to retain subscribers, don't want to necessarily focus on page views, which is what the media industry currently fixates on. Instead, what you want to do is focus on the number of days that someone reads your newspaper or your news product per month. And so the story that I've been telling is, here's a very simple graph that illustrates the importance of focusing on regularity. So if I'm reading you 0 days per month, the probability that I cancel is almost 1. Okay, so you're almost certain to lose me if I'm not reading you very often. If you can get me to read just a little bit, look at how quickly this curve drops. And then maybe it flattens out a little bit, and if you can get me, so 10 days a month would be once every 3 days. If you can get me to read more often, the function continues to go down. And so, the nonlinearity is somewhat interesting here. And so I've been showing this graph to audience as a way to emphasize the importance of making sure readers read regularly. Well, a question that usually comes up is, okay, you got this magical spline. What's the equation of this curve? What is this blue thing that's so conveniently finding the center of the scatter plot for me? So the answer to that question is not simple, and I'm going to take you through take you through how that equation actually works. So you probably watched my previous 3 videos on the subject, but let me kind of start out by building up to how this is going to work, and I'm going to talk us through it in very simple terms, and then we'll get to the equation. So let's just look at your usual scatter plot that I've been having, where maybe I've got some nonlinearity in there. And so where we started this unit was with a bin smoother. Bin smoother says, go make some bins. And then the idea is to fit a function locally. So we're going to fit some sort of function f1 hat locally to approximate our true f. So you can think of this as your true f, the true f. So remember, my model is this: y equals f at x plus some errors. Then I have some other function f hat 2 at x that works in this local area, and some function f hat 3 at x that works in that area. Maybe I need to make this a little bit bigger for you. So we start out with bin smoothers. Bin smoothers say, fit a piecewise constant model in each bin. So in other words, f hat 1 at x is just going to be some constant, say beta 1. And so that would be beta 1. Then what we did was we said we could do a piecewise linear fit to this. So I can do better than just having a constant in each region. Why don't we stick a line in there? So I'm going to fit the best least squares line here. Okay, and maybe that's that line. Then I'm going to fit the best least squares line here, and I'm going to do so under the constraint that they match up at this point called a knot. So there's another piecewise fit. And then we're going to do the exact same thing out here in this third bin or neighborhood and fit another line. So I've got 3 lines, and that's my fit. That's the piecewise linear model. Where we're going to go next is we're going to go a step further. So we could think about the f hat x1 as being some beta naught comma 1 plus some beta 1 comma 1 times x in that region. So that's the piecewise linear. We're now going to do the next natural thing, which is to fit a more complicated function in each one. I'm going to put a cubic in there. So here's my cubic. So beta naught comma 1 plus beta 1 comma 1 x plus beta 2, beta 2 comma 1. So that 1 refers to which bin I'm in, x squared, plus beta 3 comma 1 x cubed. So in each one of these regions, I'm gonna give myself a little more flexibility. So it doesn't have to be a straight line, but I'm gonna impose all sorts of constraints. So constraint number one, my overall f hat is continuous. So in other words, I can have a cubic spline here and another cubic spline here, but they have to match up at the knots. Is everywhere continuous? You know, and what I'm really saying here is at the knots. K-N-O-T-S. So this is my knot C1, this is my knot C2. Constraint number two is that the slope of f hat at x is continuous. So in other words, what I'm really saying here is, if I take the derivative of some fk at x, well, let me, this is C1 and this is bin 1. So if I evaluate f hat k at C1, all right, and that's the derivative. So the derivative of this function has to match the derivative of the next function. So k plus 1 evaluated at ck. So in addition to having a continuous function, the slope has to be continuous. So there can't be any discontinuous jumps. So, you know, I can see the slope has changed there. Whereas if I had a function here and it carried on, you know, what I meant here at the knot, the slope is changing in a very continuous way. There is no discontinuous jump where the slope all of a sudden becomes something very different. So we could say this is bad and this is good because my slope is continuous. Now, people always ask, why do we use the cubic? The reason we're going to use the cubic is because the human eye can actually detect changes in the curvature. So we're going to make the curvature of f hat at x be continuous. That's f hat. Be or is continuous. Let's say is continuous. So what that means is if I take the second derivative, so this is the second derivative of one of my polynomials in that region, and I evaluate that at a knot, that has to be the same as the second derivative at the next function evaluated at that same knot value. So when I'm going to have a cubic function here, and I have another cubic function here, but they have to match. The slope has to be smooth, and the curvature has to be smooth. So no discontinuous jumps in either of those. So if I have a function like this, it is called a cubic spline. So a linear spline was the red line, where it's continuous, but I don't worry about my slopes or my curvature. Cubic spline, I have to worry about continuity, the slope, and the curvature all matching up at those knots. So the question I started out with is, what is the equation of this thing that's so wonderful? The answer is, well, if I did what I just said on this paper, there would be some knots. You know, so maybe I have a knot at 5, 10, and 15, and I'd have one cubic polynomial here. I'd have the equation of another cubic polynomial here, another one here, and another one here. So maybe I have 4 equations that I would have to use. We're going to see in a second that that's not quite what R does, but that's the basic idea. Okay, so this slide basically says what I said on the paper. So the idea is, you know, in general, I'm going to have k knots, and I'm going to define some chunk f, hat f hat k at x. F hat k is only defined on my kth bin. And what sorts of constraints do I have? Well, f has to be continuous, so do the first two derivatives. And if you read Hasty, Tibshirani, and Friedman, which is the more advanced book that our authors wrote, they just mention that the reason we do this is because the human eye can detect these other changes. So let's go try this for the simplest of cases. So let's go back to that example that I used for piecewise linear splines. But and the piecewise linear spline that we found earlier is this red one. And I'm going to give myself a cubic spline, and you can see this is a very nice smooth curve. So it's kind of amazing how we we can produce such a nice smooth curve automatically. So how do we do that? Well, this is our output from R, and I'm going to go over here and let's go write out the equation. So the equation is going to be y hat is equal to, I'm going to round that intercept to be 0.20, and then plus 0.06 times x, or this is we had the amount of news that you consume as an index on the x-axis and your civic participation on the y-axis. Then we have a minus 0.025 times x squared. We have a plus 0.0027 x cubed. And then we have plus 0.0012 times x plus cubed. And so what is x plus? This is equal, so x plus is equal to x for x greater than or equal to 0 and is equal to 0 otherwise. And so if you want to know what is the equation that we have, you can think of, well, f hat 1 at x is just, well, 0.2 plus 0.06x minus 0.025 x squared plus 0.0027x cubed, while f hat 2 at x, but by the way, there's a plus 0. So why is there plus 0? Because I probably should have said this, f hat 1 is for x less than 0. So for x less than 0, that last term goes to 0. Let's do f hat 2. So for x greater than or equal to 0, what you end up with is f hat 2 at x is really just f hat 1 at x plus the last term. So 0.0012 x plus, well, we don't need the plus anymore because we've assumed that x is positive, therefore we just drop in x. Now, I don't think I want to do this in this video, but what would be a useful exercise for any of you who remember your calculus, this is not hard. What you should do is find f hat prime 1 at x. So find these. This is sort of an exercise for you. And also find f hat prime 2 at x. So you're going to just take the derivative of this with respect to x, take the derivative of that with respect to x. And what you should do then is show that, for not C1, which was equal to 0, I want you to show that f hat 1 prime at 0 is just f hat prime 2 at 0. You should also show that f1 at 0 is equal to f2 at 0. And if you do the second derivative, the second derivative should also be continuous at 0. And so this establishes what my claim is about this spline. What makes the spline so attractive is that the slope doesn't change. It changes in a continuous way. There are no sudden jumps in the slope. And the second derivative, which reflects the curvature of your function, also changes in a nice, smooth way. There are no discontinuous jumps anywhere. So it's fairly easy to take the derivative of a polynomial and then just drop 0 in, and it works. Well, all right. Let's go look at this for the wave this is the sine wave. And remember, I made this problem especially difficult for myself because I only gave myself 30 data points. If I'd given myself 100 data points or 1,000 data points, this would be a pretty easy problem. But with only 30 data points, it's pretty hard. A neural network would have a lot of trouble with this. A tree would just completely fail with only 30 data points. A neural network with 1,000 data points would probably do just fine. So here's how I can introduce these. I'm going to have knots at 1 and 2 as I did before. And this is the way I can introduce that x plus function. So we're just going to add this I of, well, whenever x is greater than 1, I want you to have x minus 1 cubed, otherwise make it 0. Likewise, we're going to do the same thing for the other knot. Here's the output I get, and I've written out the equations just as I did over here for the news consumption example. So what is the equation in the 0 to 1 area? Well, the answer is just take your first 4 terms and multiply them by the respective coefficients, and that's what you get right here. Note that when x is less than 1, this term drops out because x is not greater than 1. Likewise, this term drops out because x is not greater than 2. Then what happens to us when we're in the second bin? So we're between 1 and 2. Well, you get the same thing you had before, but now this term will not be 0. So this x greater than 1 is true, so that evaluates to 1 times x minus 1 cubed. And so you see I've just written this out. So there's x minus 1 cubed times the estimated coefficient, which is sitting right here. What about for this last bin? Well, the answer is now you have to have all 3 of them. So that's a long answer to my question. What's the equation of this curve? But that is the answer. So you need to stitch together a bunch of cubic polynomials, and you have the answer. Well, I mentioned that this works, but it's not the way R does things. So you may be wondering, what's wrong with this? I mean, we're getting an amazing fit to this spline, to the sine wave here. What's wrong with this? Well, the problem is you end up with a lot of terms like this. You have cubic terms. And cubic terms are problematic from a numerical point of view. So what happens is if you have a big number, so x is far from the knot, and you cube it, you end up with a very big number. So let's say I had a number like 10. 10 isn't even that big. Well, 10 cubed is, 10 squared would be 100. 10 cubed would be 1,000. Likewise, if I had an x that was very close to the knot, let's say it's 0.1 away. Well, if I take 0.1 cubed, I end up with 0.001, which is a very small number. So these cubic functions mean that you end up with a lot of very small numbers and a lot of very big numbers. And we're going to be doing a lot of arithmetic internally to compute the least squares estimates with these. and you end up with rounding errors, especially if you're using single precision arithmetic. All those very small numbers just get lost when you add them to very big numbers. And so this well-known problem, and one of the best solutions is to find a different representation called a B-spline that doesn't have these same numerical difficulties. So you should know the term B-spline. You'll see it often in software. And what you should think about when you see the word B-spline is it's one of these cubic splines, but it behaves well computationally. So don't worry about exactly what a B-spline is. You can read about it on Wikipedia if you want. But it's just a stable way to represent a spline. Now there's a lot of other versions of splines, just slight variations of this. So one is called a natural cubic spline. And so what a natural cubic spline does is it constrains f to be linear if you're outside of your knots. Okay, so if you're going to extrapolate, extrapolate with a line. Don't extrapolate with some very curvy, cubic polynomial. And so that's what a natural spline is. So if there's any, I wouldn't recommend extrapolating at all with splines, but if you had to, you'd want to use a natural spline. I'd much rather have a parametric functional form if I had to do some extrapolation. Yeah. Now, the flexibility of this is going to be determined in part by the number of knots that we have. That's the main smoothing parameter. There's another problem that we have with what we've been talking about, and that is, where do I put my knots? And so that's kind of an arbitrary decision. Is there a reason I should have put my knot at 1 and not at 0.9? So to avoid these problems, what's usually used in software is something called a smoothing spline. And so I want to talk a little bit about what a smoothing spline is. So smoothing spline is where you have a lot of knots, and you give yourself enough knots that you're just ready to overfit. You've got so much flexibility in your function that it's going to overfit. But then what we're going to do is moderate how curvaceous that function is with a penalty term. So we're going to use penalized least squares, just as we did with ridge regression. This looks a lot like ridge regression or lasso, but ridge and lasso are putting penalties on the slopes, so the first derivatives. What's going to happen here is we're going to put a penalty on the second derivative. So remember, the curvature of a function is indicated by the second derivative. And if I integrated the second derivative squared over my entire range, that's going to be a measure of the aggregate curvature in my function. Now I'm going to put a lambda penalty on this, just exactly the way I do with ridge and lasso. And let's just think about what would happen if I made lambda very big. So if I made lambda, 100 billion, then what that says is any curvature in my function is going to be severely penalized. So if this thing is at all non-zero, then we're going to take a small positive number times an absolutely massive number, and it becomes absolutely massive. So any non-zeroness in the second derivative is going to be severely punished. So therefore, what would you do if you were a good optimization routine? You would drive your second derivative to be everywhere 0. Well, what sorts of functions have a second derivative that is everywhere 0? The answer is a line. So let's just take a nice line here, beta naught plus beta 1 times x. And so let's take the derivative. dy dx, which would be, you could call this is your f prime at x. And so f prime at x is, well, beta 1. Now let's go take our second derivative. What is the second derivative of this? The answer is 0. So in other words, if I have a function that looks like this, f prime prime at x is 0. There is no curvature. I meant this to be a straight line. There is no curvature to this. Therefore, when I compute this penalty over my a to b, so maybe I'm trying to approximate my function from here to here, well, since there is no curvature there, I pay no penalty. So the point I'm trying to make is when lambda is very big, I get a straight line. If I make lambda, say, 0, what's going to happen? Well, I've got a very flexible f hat because I gave myself a lot of knots. And so this thing can wiggle all it wants, and you'll get something that follows every wiggle in the data. So what we've just done is found another way to control the bias variance trade-off. It's very similar to what we've done with ridge regression. Giant lambda means simple function. Tiny lambda means let it be complicated function. So it's exactly the same thing with smoothing splines, except we're putting this this penalty on the second derivative instead of the first derivative. Just remember what was your ridge penalty? The ridge penalty was this: minimize the sum of squared errors, so residual sums of squares, plus lambda times the sum j equals 1 to p beta j squared. So that was the ridge penalty, which is a function of the first derivative of your function. This is the second derivative for the splines. All right, that's probably a good place to stop right now. In the next video, we're going to come back and I'm going to talk about applying these splines in practice.